They're certainly not going to be long questions. Well, if they are long questions, there'll only be one or two of them, rather than three. If there's going to be three questions, they'll be short questions. The quizzes are not designed to be difficult. They're designed to, give you something to show that you've, learned the material so far. Just your understanding of that. Why is the... Oh, I must have turned the projector off while I wasn't looking. Anyways, projector's warming back up. So I'm just going to quickly, before I get back into the material, just sort of talk about where we're at and where we're going. So far we got about halfway through section 5.3 last class. Again, section 5.3 is the fundamental theorem of calculus. And we talked about last class the first part of the fundamental theorem of calculus, which is, I guess that's counting down, and then when it's finished counting down, it'll show us something. So what I talked about last class was the first part of the fundamental theorem of calculus, which tells you how do you evaluate something like this, right? How do you calculate the derivative of the integral from 1 to x of this thing? And the answer is, if you want to take the derivative of an integral, basically the derivative and the integral sign will just cancel each other out, and the derivative will just be sine of x squared. So we'll just take the x that's up top, plug it in for t in the function on the inside. And that this thing doesn't change if the bottom limit of integration changes. If this is a 1, still sine x squared. If this is a 7, still sine x squared. If this is a 10, this is still sine x squared. And the reason for this is that if we have the integral from 1 to x, we're talking about this area, right? If we have the integral from, let's say, 2 to x, we're talking about that green area. And the difference between the black area and the green area is just whatever this area is. The difference between the black area and the green area is a constant, right? So if we have the integral from 1 to x squared and the integral from 2 to x squared, they differ by a constant. The derivative of that constant will be 0. Yes?
Just to clarify, it won't change if it's continuous there. But if there was a discontinuity,
yes,
then it's not going to work. But I guess one of the questions that came up when I was going through the homework is, could you have a function that is discontinuous somewhere, but set the limit of integration past the discontinuity and still evaluate?
The answer is yes. What you'd have to do is you have to split up into two separate integrals. Okay. So the one thing Daryl just mentioned is the fact that this thing only holds true in the textbook if this function is continuous. Now, all the functions we have formulas for are continuous. So as long as it's been, all the functions that we have formulas for are continuous on their domains. So as long as there's not like a vertical asymptote or something in the middle, we don't have to worry about that. We will have to worry about things if there's if there is, let's say we're talking about the function 1 over x. Okay, I need a different black marker. The function 1 over x looks like this. It's a discontinuous function because it's got two different pieces to its graph. It turns out that if we have, negative 1. If we have this thing, then you go from negative 1 to x of 1 over t dt. This guy is going to behave a little bit more weirdly than the integral from 1 to x would. And that's because of this discontinuity, because of that vertical asymptote there. Now, the way to deal with this is to actually just figure out what this area is, subtract this area from this one. Or, so all the way up to 1. Get rid of this green area, and then deal with this part separately. And we'll talk about that a little bit more later in the course. And if you don't understand what I'm talking about, that's okay, because we haven't actually sort of gotten there yet. But the answer is, if you do have a function which is discontinuous, there are other methods we need in order to deal with the fact that there is a vertical asymptote, that there is a discontinuity in the function. And that will come up in Chapter 7. For now, everything I'm going to give you is going to be continuous, so you won't have to worry about that. Okay. Oops, not group problems yet. I need to go to 5.3, back to 5.3. So, okay. So last class we talked about the fundamental theorem of calculus part 1, right, which was this thing that said we can take the derivative of an integral by taking the upper limit and plugging it in. What we're going to be talking about is the fundamental theorem of calculus part 2, sort of the second half of it. And this part is going to be the more useful part of the fundamental theorem of calculus. This one's going to allow you not just to take the derivatives of integrals, but to actually evaluate integrals, to actually say, okay, what does this integral give you? How many people here already know how to evaluate this integral here, integral like that, from previous courses? Good part of the class. How many people have learned this at some point in the past and forgotten it? Great. How many people have never seen something like this before? Okay. There's a few in each camp, which is what I'm expecting, what I've sort of planned for. So the key thing with integrals like this is that if you remember what I talked about last class, I said that if we have the velocity of an object and if we have the position of an object, we can go from the velocity to the position by integrating. We can go from the position to the velocity by differentiating. Right? Now, it turns out that if we integrate the velocity, we don't quite get the position. We get what's called the displacement. Right? We get sort of like, how much has the particle traveled in that time. Right? So if you remember, if I take a velocity of a particle, and if I integrate it from A to B, I'm sort of measuring the displacement over a whole bunch of different intervals and adding up all those different intervals. So dividing, again, those rectangles represent, how much has it traveled over this unit of time, how much has it traveled over this unit of time, how much has it traveled over this unit of time. If I add those all up, that gives you the total distances traveled. One way of measuring that total distance traveled is to take the position at the end and subtract the position at the beginning. So you can say that if we integrate the velocity, we get the position at the end minus the position at the beginning. Now the velocity here is the derivative of this position function. So the idea is if we integrate a derivative, we get whatever the original function was at B minus the original function at A. Now what this statement that I have written up here is true for any function x. The position function could be anything, and this statement would still be true. What that means is if I want to integrate something inside here, all I've got to do to integrate it is figure out what is it the derivative of. So if I want to integrate 2x, I've got to figure out what is 2x the derivative of. 2x is the derivative of x squared. So that means my x of t function is x squared. Right? I'm just going to do x squared at b minus x squared at a. So that fact is what's called the fundamental theorem of calculus part 2. It says if we want to integrate a function, f of x dx, what we've got to do is we've got to find some other function which has that function as its derivative. We've got to find an antiderivative. Once we've found an antiderivative, all we've got to do is we've got to plug in the top endpoint into the antiderivative, plug in the bottom endpoint into the antiderivative, and subtract. So that's what the fundamental theorem of calculus part 2 says, is if you want to integrate a function, you've got to find the antiderivative, plug in the two different endpoints into that antiderivative. One thing to mention, and again, this is something that's in the textbook, and I didn't write it on the slides because I didn't want to sort of have to worry about that yet. But the thing to mention, the fundamental theorem of calculus only works if f of x is continuous. Between a and b. So again, if I had that example of 1 over x, right, and I wanted to integrate it from -1 to 1, here between -1 and 1 there's a vertical asymptote in this function. It's not continuous between -1 and 1. So we actually cannot do this integral using the fundamental theorem of calculus. We will need other methods to do it. But as long as the graph of the function doesn't have any vertical asymptotes in the middle, then we can do this. One way of thinking about it is, again, my argument as to why this thing is true came from physics. This doesn't really describe a physics situation. Physics things don't have vertical asymptotes for the most part. You know, you don't have a physical quantity jumping from way down here to way up there. Doesn't really happen physically. The only examples I can think of are things like electric field, or no, magnetic field on either side of a magnet. Anyways, there's weird things like, but those are only approximations to the truth anyway, so don't worry about that. Or black holes also have vertical asymptotes. Again, there's really weird physical situations which do, but normal physical situations don't have vertical asymptotes. So, anyways. But again, this only works if it's continuous. I'm not going to ask you to use it in situations where it's not continuous, but later on we'll learn how to deal with vertical asymptotes. Any questions about what this thing says before I go on to examples of using it? Great. Okay. So the idea is what the fundamental theorem of calculus part 2 says is if you want to evaluate an integral, we've got to find the antiderivative, we've got to plug in the top end point, we've got to plug in the bottom end point. The symbol we oftentimes use for doing this looks like this. Oftentimes we draw a vertical line. We figure out what the antiderivative is, and then draw a vertical line after it and write the top end point up here and the bottom end point up here. That just symbolizes that what we're going to do is we're going to take this thing, plug it into the function, then take this thing and plug it into the functions. So when I'm doing problems involving this, we're going to see that symbolism. We're going to see me using those symbols. So here in example 6, we have an integral we want to evaluate. So here we have the integral from 0 to pi over 4, secant theta, tan theta, d theta. So the first thing we do if we want to evaluate an integral is we look at the thing inside and say, okay, what is this thing the derivative of? What's an antiderivative of this? Well, secant theta tan theta is the derivative of secant theta. So if we want to integrate with this thing, what we're going to have to do is we're going to have to take secant theta, we're going to have to plug in 0, and we're going to have to plug in pi over 4. And that's where this sort of vertical bar afterwards, this is where this comes in. It is sort of a way of representing, okay, these are the two numbers I'm going to have to plug in. I'm just going to write them down here. And then the next step is going to be to actually plug these things in. So I'm going to take secant of pi over 4 minus secant, 0, not theta. 0. So I plug in the top, I plug in the bottom, I subtract. Now, if we want to calculate secant of pi over 4, just remember that secant is 1 over cosine. Secant of 0 is 1 over cosine of 0. Cosine of pi over 4 is square root 2 over 2. Cosine of 0 is 1. And if we're taking 1 over a fraction, it's the same thing as flipping that fraction. So 1 over square root of 2 over 2 is 2 over square root of 2. 1 over 1 is 1. And that's the one possible answer. One thing to mention, 2 over square root of 2 is actually the same thing as square root of 2. So if you wrote it like this, that is also correct. I don't care whether you write it like this or like this. One thing I don't want you writing it as 0.4. Because when you've written it as 0.4, even if you've written it as 0.414, you've still given up on some information. You've lost the information of what happened after this third decimal place. So this is what's called a numerical answer. This is what's called an exact answer. For these sorts of questions, I always want exact answers. So please give exact answers unless you specifically say, use a decimal approximation for this question, or very specifically say, find a numerical answer. One thing to mention is numerical answers can be found using, one of the reasons I ask for this rather than this is because numerical answers are things that are really easy to do just using rectangles. You can get an answer that's correct to 3 decimal places if you use enough rectangles. And there are graphing calculator programs out there that will do the rectangles for you. So you can get this sort of thing from your graphing calculator without actually finding an antiderivative. This sort of thing you can't get without actually finding an antiderivative. That's the idea. So that's why in this course we want these answers. It's because these are the ones that actually come from this method of finding antiderivatives. Sorry, this is example 6. I didn't label it when I started. Any questions about example 6 here? Yes?
An easy way to figure out an exact answer for what cos pi over 4 is?
Yeah.
Or maybe just have to memorize that.
The unit circle, right? So there's 3 special angles in the unit circle that you need to know. Those special angles are pi over 6, pi over 4, and pi over 3. Oh, sorry, no. If we want to know what their x-coordinates are, this is going to be the smallest x-coordinate, this is going to be the biggest x-coordinate. So we can just count them off 1, 2, 3 like this. If we want to know what the y-coordinates are, this is going to have the smallest y-coordinate, this is going to have the biggest y-coordinate. So I go 1, 2, 3 like this. Then the rule is take the square root of everything, divide it all by 2. Square root of 1 is just 1. Square root of 2 is square root of 2. Square root of 3 is square root of 3. Sorry, that 3 is ugly. Square root of 1 is just 1. This is square root of 2. This is square root of 3. If I divide it all by 2, I'm going to do this again on the other side of the board where I have more space, because I realize that looks really ugly. So the answer is, and then the cosine is just the x-coordinate. The sine is just the y-coordinate. So cosine of pi over 4 is this x-coordinate, square root of 2 over 2. Sine of pi over 3 is square root of 3 over 2. Again, let me just do this quickly again. So again, there's 3 special angles on the unit circle that you do need to know. Pi over 6, pi over 4, pi over 3. This is the smallest x-coordinate, this is the biggest one, so I can do 1, 2, 3. This is the smallest y, this is the biggest y. Do 1, 2, 3 like this. Square root of everything. Divide it all by 2. By the way, this method also works if you want to know this point and this point. This point's before 1, so it's 0. This point's after 3, so it's 4. This one is 4, 0. If we take the square root of 4, it gives you 2. If we take the square root of this 4, it gives you 2. Divide it all by 2. 2 divided by 2 is 1. 2 divided by 2 is 1. So if you need to know these points as well, like pi over 2 and 0, you can also do 1, 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, and do the same method. Yeah, I was going to say the square roots and stuff happen because of the Pythagorean theorem. That's where the square roots come from. The dividing by 2 comes from because we're counting from 0 to 4, which is from 0 over 4 to 4 over 4. If that makes sense. And the square root of 4 over 4 is 1. If you take the square root of top and bottom, that gives you the 2 on the bottom. So it's sort of like thinking we're counting from 0 quarters to 3 quarters and we're taking square roots, is another way of thinking about that. But, yeah. Anyway, so the answer is that you should know these guys. This is sort of something you should have learned in high school. And again, to find exact answers, you do sometimes need to know these things. But there are easy ways of memorizing them. Any other questions before I move to the next slide? Okay. So the next slide deals with more complicated integrals. So the last one was one where, okay, we just knew what the antiderivative of secant theta tan theta was because it was a simple derivative formula. More complicated things, we're going to need more complicated things to work with. But the more complicated situations we're going to deal with in the same way we dealt with the more complicated antiderivatives back in section 4.9. So for example, if we have a couple things added together, we can do their antiderivatives separately. If we have constant times something, those constants are going to stay. If we have, if we have two things multiplied together, we expand it and then take the antiderivative. If we have something divided by something else, we divide each thing by that thing and then take the antiderivative. So here's an example of a bunch of different integrals we can do using this method. So first one is example 7. Here we have the integral from 0 to 1, 1 plus a half u to the 4th minus 2/5 u to the 9 du. So the key thing to remember is we just take the antiderivative of this. We have something plus something minus something else. We can do each of the antiderivatives separately. The antiderivative of 1 is u. The antiderivative of a half u to the 4th is 1/2 u to the 5th over 5. Right, the 1/2 is a constant, it stays. U to the 4th goes to u to the 5th over 5. The 2/5 here stays. The antiderivative of u to the 9 is u to the 10 over 10. And then I put the vertical bar and I put the 1 and the 0. One thing to mention is that if you're putting a vertical bar in here, you do not need to put on the plus c. Because once you plug in these things and subtract, it'll actually eliminate the plus c's anyways. So you don't have to worry about them when you're doing these sorts of problems. So if there's a vertical bar, there's no plus c. That's sort of a quick way of remembering things. So I'm going to plug in this one, and subtract. So I'm going to have 1 plus, this is 1 over 10. I plug in 1 to here. This one's going to be 2 over 10. This is going to be 1/25. If I plug in 1 to this guy, it'll be 2 times 1 to the 10, which is 2 over 50. 2 over 50 is 1 over 25. And then I'm going to subtract. I'm going to plug in 0. If I plug in 0, I'm going to get 0 here. 1/2 times 0 to the 5th over 5 is 0. 2/5 times 0 to the 10 over 10 is 0. So 1 plus a 10th minus 25th minus 0. 1.1. 1 over 25 is 0.04. 1.1 minus 0.04 is 1.06. If you wanted to write this as 53 over 50, that is also correct. The key thing here is in this case 1.06 is an exact answer because I haven't chopped off any decimal places. This is exactly 1.06. So there are situations where a numerical answer is also an exact answer, and that's okay, right? As long as you don't chop off decimal places, you're fine. But if you have a decimal that keeps on going and going and going, and you only keep the first 10 decimal places, you've chopped stuff off. So either 1.06 or 53 over 50 are both correct answers to this problem. Any questions about what I did here? I'm oftentimes in these sorts of problems going to skip the actual computational steps because that's just calculator work. So again, these numbers just come from plugging in 1. These numbers come from plugging in 0. Hopefully you can do those in your calculators fine. If I do make mistakes, please let me know. So please sort of check these steps in your calculators. But yeah, I'm not going to show all the calculator steps. So example 8, here I have the integral from 0 to 2, y minus 1 times 2y plus 1 dy. So the key thing here is before I take the antiderivative, I'm going to need to expand this guy. So expanding it, I may get 2y squared minus 2y. Y times plus 1 is plus y minus 1. And I can simplify that. Minus 2y plus y gives you just minus y. So I have to integrate 2y squared minus y minus 1. Integrating 2y squared will give you 2y cubed over 3. Integrating y will give you y squared over 2. Integrating 1 will give you y. The numbers I have to plug in are 0 and 2. I'm going to have to continue it up here because I've run out of space on that board. So when you plug in 2, that's what I get. 2 times 2 cubed over 3 minus 2 squared over 2 minus 2. If I plug in 0, I get 0 minus 0 minus 0. This is 16 over 3 minus 2 minus 2, which gives you 4 over 3. Each of these 2's is going to be 6 over 3 subtract 6 over 3. Once I get 10 over 3 subtracted again, I get 4 over So the value of this integral is 4 over 3. Any questions about example 8 here? One thing I want to mention about how I'm writing this out is that any simplification I'm doing inside the integral, as I'm doing it, the integral sign will stay in front. Once I have done the antiderivative, then I can get rid of the integral sign and replace it with the vertical bar at the end. Okay. So the last one I'm going to do is example 9. Here we have the integral from 1 to 2, 4 plus u squared over u cubed du. Now here, if we have something divided by something else, again, we're going to need to simplify before we can integrate. We can't integrate something divided by something else without simplifying first. So the way I'm going to simplify is I'm going to write it as 4 over u cubed plus u squared over u cubed. 4 over u cubed can be written as 4u to the negative 3, right? Then that will be something we can find an antiderivative of. U squared over u cubed can be written as 1 over u, right? Cancel from the top and bottom. Now, if I want to do the integral of 4u to the negative 3, or the antiderivative of 4u to the negative 3, the 4 is going to stay. The u to the negative 3 will become u to the negative 2, and I'm going to have to divide by negative 2. The antiderivative of 1 over u is ln of the absolute value of u. Again, I mentioned this before. The antiderivative of 1 over x is ln of the absolute value of x. You can't do x to the 0 over 0, because that would involve dividing by 0. And then you've got to plug in 1 and 2. So when you plug in 2, you're going to have 4 times 2 to the negative 2 over negative 2 plus ln absolute value of 2. And if we plug in 1, we're going to have 4 times 1 to the negative 2 over negative 2 plus ln absolute value of 1. 2 to the negative 2 is a quarter. 4 times a quarter is 1. 1 over negative 2 is negative a half. Absolute value of 2 is just 2. Here, 1 to the negative 2 is 1, 4 divided by negative 2 is negative 2, negative negative 2 is positive 2, and ln of 1 is just 0. So this will be 3 over 2 plus ln of 2 once it's simplified. One thing to mention about these guys is oftentimes it is okay just to leave your answer like this. Again, oftentimes I will not be, especially with some of the more complicated ones, I will just leave it like this. So as long as we have some, even if it's a really complicated number, as long as it's something we could evaluate by typing into a calculator, I'll be okay with that. You don't necessarily have to simplify it down to this guy if you don't want to. There are some exceptions to this, which is like if the whole thing gives you 0, I want you to show me that the whole thing gives you 0. Or if there's things that cancel, I want you to cancel those things. But otherwise, you know, figuring out what this guy gives you, figuring out what this guy gives you, not that important. Okay. Any other questions? Okay. So take a 10-minute break. We have now finished section 5.3.